If you could go back about 1,000 years and walk through the right workshop in China, you'd find a group of alchemists doing something that had nothing to do with weapons. They were trying to make an immortality potion. The specific combination they were experimenting with was charcoal, sulfur, a crystallized salt called potassium nitrate, which they'd been collecting from bat droppings in soil for years. They had no interest in killing anyone. They were looking for a way to live forever. What they accidentally made instead was gunpowder. It would eventually reshape every war, every border, and every power structure the world had ever known. The story of how a pursuit of eternal life became the foundation of the deadliest weapons in human history is one of the stranger threads running through the whole record of civilization. The Chinese had been documenting chemical experiments for centuries before the actual discovery happened. Taoist alchemists during the Tang dynasty, roughly the 9th century, were mixing substances and heating them in search of an elixir. At some point, someone combined charcoal, sulfur, and saltpeter in the wrong proportions and set it on fire. The results were immediate and hard to ignore. The mixture didn't just burn, it deflagrated, releasing energy fast enough to produce a sudden burst of heat, light, and pressure. Early texts from the period describe it as a fire that couldn't be controlled, burning the hands and faces of the people who made it, sometimes setting the whole building alight. That was the first clue that this wasn't medicine. It was something else entirely. Within a few decades, the military applications were obvious to anyone paying attention. By the late 9th and early 10th centuries, Chinese engineers were packing gunpowder into bamboo tubes and attaching them to arrows. When the arrow flew, the powder ignited and extended the fire across a much greater distance than any conventional projectile could. These were called fire arrows, and they weren't subtle. They were used to set enemy fortifications, ships, and supply stores on fire from a safe distance. That was a significant tactical advantage when siege warfare required getting dangerously close to the walls you were trying to take down. But fire arrows were still basically just delivery mechanisms for flame. The idea of using a contained explosion to destroy something hadn't fully arrived yet. That step came during the Song dynasty, somewhere around the 10th and 11th centuries. It came from a simple observation. If you seal gunpowder inside a container and ignite it, the pressure builds until the container can't hold anymore. Then it doesn't just burn, it shatters. Early Chinese bomb makers started filling ceramic and iron shells with gunpowder, packing them tightly, sealing them with a fuse made of twisted cord or bamboo, throwing them at enemies or launching them with catapults. These were the first true bombs, in the modern sense. Devices designed specifically to explode outward and cause destruction through pressure and fragmentation. Some variants were filled with iron shards to maximize what we'd now call the shrapnel effect. Others mixed in toxic compounds to produce choking smoke. The level of deliberate engineering involved was remarkable for a period that most people imagine as purely medieval. By the 12th and 13th centuries, the technology had spread beyond China's borders. Mongol expansion carried knowledge of gunpowder west across Central Asia. Arab scholars and military engineers encountered it through trade and conquest and began developing their own variations. Islamic texts from the 13th century describe recipes for gunpowder and mention devices called madfa, early precursors to hand cannons that used the explosive force of burning powder to propel projectiles. The transfer of knowledge wasn't always direct or acknowledged, but the underlying chemistry was the same wherever it showed up. Saltpeter, sulfur, and charcoal in roughly the right ratios will produce the same reaction whether you're in Hangzhou or Cairo or Baghdad. Europe got serious about gunpowder in the 13th and 14th centuries. The person most associated with its early study in the West is Roger Bacon, an English friar who described the composition of gunpowder in coded form around 1267. Whether Bacon fully understood what he had, or was just documenting something he'd encountered through Arabic texts, is debated. What's clear is that within a generation of his writing, European armies were starting to experiment with cannon. The first cannons were crude by any later standard, basically iron or bronze tubes packed with powder and a stone or metal ball, mounted on a frame and aimed at walls or ships. They were unreliable, slow to reload, and occasionally just as dangerous to the person firing them. But they worked well enough that everyone wanted them. The hand-thrown bomb took longer to evolve in Europe than the cannon did, mostly because cannon were simply more useful for the kind of siege warfare that dominated the period. But by the 15th and 16th centuries, soldiers were using iron spheres filled with gunpowder and a burning fuse, the direct ancestor of what we'd recognize as a grenade. These were called grenades, from the French word for pomegranate, because of the rough resemblance in shape. Early versions were genuinely hazardous to use. You lit the fuse. That was essentially a length of cord. Then you had to throw it far enough before it went off in your hand. The fuses were inconsistent. Some burned faster than expected. Some burned slower, which was also a problem because it gave the enemy time to throw it back. Timing was everything, and timing was exactly what you couldn't control. Naval warfare pushed bomb development in a different direction. Ships were floating wooden structures packed with supplies, crew, and ammunition. That made them extraordinarily vulnerable to fire and explosion. By the 17th century, naval gunners were using hollow iron shells filled with gunpowder that were designed to penetrate a ship's hull before the fuse ignited. The idea was to blow apart the structure from the inside. Loading and firing these shells required considerable skill because a mistake in the timing of the fuse could detonate the shell while it was still in the cannon, which was catastrophic. Despite that, the explosive shell became a standard feature of naval artillery throughout the 17th and 18th centuries. The arms race between navies to build ships that could fire larger shells at greater distances drove substantial advances in both metallurgy and chemistry. Up through the 18th century, gunpowder was still the only game in town when it came to explosive chemistry. It worked, but it had real limitations. It was sensitive to moisture, it left a thick residue when it burned. The energy it released was significant but not enormous by the standards of what chemists would later figure out was possible. The shift came in the 19th century, when a series of researchers started experimenting with nitrogen-based compounds and discovered that certain combinations were dramatically more powerful than anything gunpowder could produce. The key was a process called nitration, essentially adding nitric acid to organic compounds. That created unstable molecules that released enormous energy when they broke apart. One of the first practical results of this was nitroglycerin, synthesized in 1847 by an Italian chemist named Ascanio Sobrero. Sobrero himself was disturbed by what he'd made. Nitroglycerin was roughly 13 times more powerful than gunpowder by weight, but it was almost impossibly dangerous to handle. It detonated from heat, friction, or impact in ways that were completely unpredictable. Sobrero reportedly warned others against producing it in large quantities, believing it was too unstable to be useful as anything except a hazard. He wasn't wrong. Several factories that attempted to manufacture nitroglycerin in the following years simply exploded, sometimes with significant casualties. The substance had enormous energy locked inside it, but no one had figured out how to make that energy controllable. That problem is what Alfred Nobel spent years trying to solve. Nobel was a Swedish engineer and industrialist whose family had been working with explosives for military and construction purposes since the 1840s. In 1864, an accidental explosion at his family's factory outside Stockholm killed his younger brother and 4 other workers. Rather than walking away from the problem, Nobel became more focused on it. He began experimenting with ways to stabilize nitroglycerin by mixing it with absorbent materials that would hold the liquid in place and make it less sensitive to accidental detonation. By 1867, he found that mixing nitroglycerin with a type of diatomaceous earth called kieselguhr produced a paste that was stable enough to handle, transport, and shape, but still detonated reliably when triggered with a blasting cap. He called it dynamite. Dynamite transformed construction, mining, and warfare almost simultaneously. For the first time, you could move a specific amount of explosive to a specific location, shape it to direct the force where you needed it, set it off on command. The railroads, tunnels, and canals that defined 19th century infrastructure required moving massive amounts of rock and earth in ways that manual labor simply couldn't accomplish quickly enough. Dynamite made projects feasible that would otherwise have taken decades or been abandoned entirely. Militaries noticed immediately and started incorporating dynamite and similar high explosives into artillery shells, mines, and demolition charges. The scale of destruction that became possible in warfare shifted dramatically. TNT, trinitrotoluene, was first synthesized in 1863 by a German chemist named Julius Wilbrand. Though its explosive properties weren't recognized for another 30 years, by the early 1900s, it had been adopted by the German army as a standard bursting charge for artillery shells. Other European powers followed quickly. TNT had advantages over dynamite for military use. It was more stable, it melted at a relatively low temperature which made it easy to pour into shell casings. It was powerful enough for the purpose without being so sensitive that shells detonated from routine handling. Most of the artillery used in the First World War was filled with TNT or similar compounds. The scale of that conflict gave the world its first real glimpse of what industrialized explosive technology actually looked like, in practice. The First World War saw bombs delivered from the air for the first time at any meaningful scale. Early aircraft dropped modified artillery shells by hand over the side of the cockpit, a system that was about as precise as it sounds. Within a few years, purpose-built bomb racks, aiming systems, explosive payloads had been developed specifically for aerial delivery. By the end of the war, Germany had used large bombers to drop explosives on London. The concept of strategic bombing, attacking civilian infrastructure and morale rather than just military targets, had been introduced as a doctrine. The bombs themselves were still chemically straightforward, mostly TNT-based, but the method of delivery and the thinking behind their use had changed everything. The Second World War accelerated every part of this development simultaneously. Bomb design became more sophisticated, with shaped charges, delayed fuses, and armor-piercing variants developed for specific tactical purposes. The firebombing campaigns over European and Japanese cities used incendiary bombs designed to start fires that conventional firefighting infrastructure couldn't contain. The strategic logic was brutal and deliberate, and the results were devastating. But all of that was still within the range of what conventional chemistry could produce. The atomic bomb, tested in July 1945 and used twice in August of that year, operated on a completely different principle. Rather than releasing energy through chemical reactions, it released energy by splitting atomic nuclei, a process that produced an explosion roughly equivalent to 15 to 20,000 tons of TNT from a device the size of a large garbage can. The Manhattan Project, the American-led effort that produced the atomic bomb, drew on research from physicists across Europe and the United States who had been working on nuclear fission since the late 1930s. The theoretical groundwork had been laid years before anyone built a weapon around it. What the project required was the industrial capacity to enrich enough fissile material and the engineering knowledge to assemble a device that would achieve a sustained chain reaction before it blew itself apart. The first successful test at Trinity Site in New Mexico produced a crater, a shockwave felt hundreds of miles away, a flash visible from distances that made witnesses compare it to a second sun rising. From the alchemists in Tang Dynasty China accidentally igniting a mixture of bat droppings and charcoal, to a device capable of leveling a city in a fraction of a second, the path took roughly 1100 years.